materials which we were talking about, the dimensional modeling PPTs and the data warehousing PPTs. I did forward to you, and you can just check that, right? So to start with the other thing, so yesterday we did discussed about the use of SCD type 2 and SCD type 1 and how the SCD type 1 is being stored. And the other thing is about the SCD type 3. SCD type 3 is which stores the partial history, which means what is difference between the SCD type 2 and type 3 is that SCD type 2 stores all the values. If a customer or a supplier is changing from one location to the other location more than 2 times or more than 3 times, for every change you'll have one record. Means if the supplier is changing more than 3 times, you'll have 3 records in the SCD type 2. But in the SCD type 3, you'll have only 2 values, old and new value. When you say old and new value, it will be the previous value and the current value. Suppose if the supplier changes more than 2 times, you'll not be able to track the previous to previous value. Will not be. So that's why the SCD type 3 is being considered as a partial history. For this, you need a separate design. So this kind of things, you need a separate design to use it. You need to have an extra column to add it. So let's take an example and understand how the SCD type 3 can be implemented. With the same example, so we have SCD input. So SCD input was which was having a supplier code, supplier name, and the supplier state. These are all the columns which you have it in the OLTP table: supplier code, supplier name, and the supplier state. And let's take the same examples: supplier code, and you'll have a supplier name, and the supplier state is New York, and the other one is about the target, and here this is there in the. So the same example we have taken, and next thing is about the dim supplier tree. Observe the design, like what kind of design you actually require. Design in the sense the number of columns what we are actually keeping it in the SCD type 3. You have a supplier code. You can take this as a primary key, or you can have a separate key. That's for a design. And along with this, you'll have a supplier name which stores the supplier values. And then here, when you are actually designing a SCD type 3, you should decide for what column or for what attribute you are going to track the historical data, whether it is a supplier state or the supplier name. Let's say I want to track the history for the supplier state. Then you'll have 2 columns which will store the previous supplier state. You'll have a separate column. One stores the old value, one stores the current value. So this is how you're going to design the SCD type 3. Supplier code, supplier name, supplier state, and the previous supplier state and the current supplier state. This is what the design change. So far if you see the previous examples, you had only 1 column for one attribute, but here you have 2 attributes for 2 columns for the same attribute, 2 columns for the same attributes to store the data. So even SCD type 3, what does it say is that whenever a record is new to the OLAP system, you're going to insert the data. Whenever a record is new, you'll insert the data. So while inserting previous supplier state and the current supplier state will be same. First time you're inserting the data. Whenever a record is existing and there is a change in the supplier state, and there is a change existing and there is a change in the supplier state, then you are going to update the record. There is a change in supplier state. What happens if there is a change in the supplier name? We are going to ignore it. We are going to ignore it because we are designing this kind of a dimension. We are designing this kind of a dimension only to track the historical data for a location of the supplier. So we are not tracking the historical data for supplier name. We are not tracking the historical data for supplier name, or that is your partial history for supplier name, but you are tracking only for it. So you're tracking the partial history by adding an extra column in the same table. So now here you are going to check first whether the supplier code is existing in the DIM supplier 3 or not. So this is not existing, so you're going to insert it. So first time you're inserting the data, your previous supplier state and the current supplier state will be same. That means the supplier is getting added to your business only on this day, so the current supplier state and the previous supplier state will be same, and you'll have a created date and last updated date also, which will get updated based upon the last updated date and created date will get updated, last UPD date. So it will be the system date and system date which will be there. And similarly for a target, when you are inserting, this is for your supplier target, and you have the previous supplier state is IL and the current supplier state is IL, you're going to even update the created, insert the created date and last updated date value as a system date. Assume that over a time period of time, so the Walmart supplier is actually relocated from New York to Texas. So what happens to your existing records? What happens to your records? So what happens is that your current supplier state will become the previous supplier state in the table, and the new record which will become the current supplier state. So what will happen? The current supplier state will become Texas. From this, what do you come to know? Your previous supplier state is in New York and the current supplier state is in Texas. So this is what is going to be, and for this both the previous and current supplier will be same. What happens if again he changes the location? Again, let's say again he relocated from Texas to Illinois. So in this case, what will happen? Again, your previous supplier state will become TX and the current supplier state will become IN. So likewise, you'll be changing the attributes for the supplier, but it will be your SAD type 3 will be storing only the previous record, not the previous to previous record. Suppose if I have to identify what is the location of the supplier before Texas, I will not be able to track it. That's why the SAD type 3 is called as a partial historical data, partial history, and which will maintain the old and current, previous and current value, and the other values will not be stored. And you'll come across the very rarely about the SAD type 3 as well. So SAD type 3 also rarely designed. Whenever we have to actually store the historical data, we'll go for most of the time SAD type 2 and SAD type 1 for the current information. SAD type 3 also not being used much, but as part of the syllabus, we are going to see how to implement the SAD type 3. We're going to see how to implement the SAD type 3. Right? So that is how the slowly changing dimension types are used. So before proceeding with the facts, I would like to hear if you have any questions on the slowly changing dimensions. So the slowly changing dimensions, as the name indicates, it changes over a time period of time. So whenever you are designing the slowly changing dimensions, so it should be of a type 1, type 2 or the type 3. Type 1, type 2 or the type 3. And let's understand what is a fact table now. What is a fact table? So the fact table is about which will consist of measures. A table which consists of measures. When I say measures includes your business metrics. Business metrics, something like revenue, sales, and you have a quantity, profit. All these kind of measures are called as a facts. A table which contains a measures, a table which contains a metrics, a table which contains a facts is called as a fact table. And overall, it will have a numeric data. It will have a numeric, means all the numeric data will be stored in the fact table. So whenever you are designing the fact table, you need to understand the grain of the fact table. You need to understand the grain. So what is a grain? Grain is nothing but the level of data. Level of data is called as a grain. So when we discussed about the grain, so the grain means, suppose you are storing the revenue at the year level, sales at the year level, quantity at the year level, profit at the year level, then the grain of the fact table is a year. Here we call it as a year level of data. So if you are storing the revenue at the month level, monthly revenue, monthly sales, monthly quantity and monthly profit, then that is called as a monthly grain. Monthly grain. So whenever you are designing a fact table, you should often determine the grain of the fact table to see that. Grain of the fact table to see that. So whenever you are designing, you should identify the grain of the fact table. So how does a fact looks like? So all your fact table will contain all the foreign keys from your dimensions. So this model key is a primary key from your model dimension. Dealer key is a foreign key from your dealer dimension, and time key is a foreign key from your time dimension. And it will contain the two measures, that is your revenue and fact. Both are the measures. Always your fact table will contain the foreign keys from all the dimensions and the measures. So what will be the relationship between the dimension and a fact whenever you are creating? It will always be one to many. It will always be one to many whenever you design the fact table. Whenever you design the fact table, that will be one to many. So there are different types of facts. So when I say different types of facts, do not get confused. It is not the different types of tables. It is the different types of measures. It is the different types of measures, or different types of metrics. So measures, metrics, or facts, different types of facts. You have different types of facts. You have different types of facts. So let's first consider the structure of the fact table. Always the fact table will contain the dimensional foreign keys. Let's say you have a time key, which is a foreign key from the time dimension, and you have a product key, which is a foreign key from product dimension. You have a model key, model and the product both the same. I mean, we can take about the customer key, which is a foreign key from customer dimension. Along with this, we have a few attributes like average sales and percentage of growth, and all those things. Percentage of growth, all these things. Time key, product key, customer key, average sales, and the percentage of growth. So these are called as a measures. Average sales is a measure and percentage of growth is a measure. So these measures are divided into three types. One is a fully additive measure or fully additive fact, semi-additive fact, and non-additive fact. Fully additive, semi-additive, and non-additive. Fully additive, semi-additive, and non-additive fact which will be used. So now to understand the fully additive and semi-additive fact, if a measure or a fact which depends upon all of the dimensions, in the fact table, then that is called as a fully additive fact. Measure depends on all of the dimensions. In fact table, that is called as a fully additive measure. If a measure depends upon only few of the dimensions but not all, few dims but not all, then that measure or a fact is called as a semi-additive fact or a semi-additive measure. And the non-additive is that a measure which does not depend upon any of the dimensions. Measure which does not depend upon any of the dimensions, is called as a non-additive measure. Fully additive, semi-additive, and the non-additive measure. Fully additive, semi-additive, and the non-additive measure. So fully additive measures are, if you think about the examples, average sales. Average sales you can calculate according to the time, you can calculate according to the product, you can calculate according to the customer. So the percentage of growth Growth, what is a measure which you think about? It doesn't depend upon the time. It doesn't depend upon the customer. Company's growth, let's say you're calculating the company's growth. It doesn't depend upon the customer, what type of customer he is and all those things. So which depends upon the few of the dimensions. So product percentage of growth is directly depends upon the time. We will calculate the growth of the company from time to time, but not from the product to product or from the customer to customer. So this percentage of growth depends upon the time key, but not on the product and the customer. Whereas the average sales is something that which depends upon all. So this is a fully additive fact, and this is a semi-additive fact. Semi-additive fact. A non-additive fact, examples for a non-additive fact is that, so whenever you're storing some kind of a column, something like a temperature, let's say you're storing a weather report or whatever the weather information in the fact table, that you cannot consider it as a fact. It is a non-additive fact because it doesn't depend upon any of the dimensions. Age, suppose if you're actually storing the age of the product, or age of the product again depends, or the customer age, or any something, and which does not depend upon any of them. So these kind of facts are called as a non-additive facts. These kind of facts are called as a non-additive facts. So it is not the fact table types. Do not get confused again. So it is the types of measures what you have. Types of measures what you have. These are all the three types of measures. One is a fully additive, semi-additive, and the non-additive. Now we understood about the types of dimension tables, types of fact tables, types of dimension tables, and types of what is a fact table and all those things. So the next thing is to understand what type of schemas you design, in the data warehouse. So first thing is to understand what is a schema. A schema is something which is a group of database objects. So what are the different database objects that you can design? You can design the tables, you can design the indexes, you can design the stored procedures, functions, all the things together. Views, indexes, sequences, all these objects together is called as a schema. So the group of database objects is called as a schema. So in the data warehousing, we are going to design the two types of schemas. One is called as a star schema, another is called as a snowflake schema. Star schema and the snowflake schema that we are going to design. So what is a So it's nothing but schema is nothing but where you're going to design the tables and the relationship between the tables. In the data warehouse, what kind of tables you're going to create? You hardly create the two types. One is a fact, another is a dimension, and create a relationship between the dimension. That is your star schema. So what is a star schema? Star schema is something that one or more fact tables surrounded by the dimensions. Surrounded by the dimensions in the form of a star is called as a star schema. One or more fact tables surrounded by dimensions. Star schema and the snowflake schema is nothing but you have different fact tables where you have a relationship between the fact and dimension tables. So what is difference between the star and snowflake? What is difference between the star and snowflake schema in this thing? So star schema, main characteristics about the star schema is that all the dimensions are denormalized in nature. All the dims are denormalized in star schema. So, and in the snowflake schema, few of the dimensions are normalized. Few of the dimensions are normalized in the few of the dimensions are normalized, then that is your snowflake schema. So what is the advantage of the star schema? What is the advantage of the snowflake schema? Here, so denormalization means combining of multiple entities into a single entity. Normalization means dividing a entity into multiple entities to eliminate the duplicates. So that is normalization and denormalization. Now let's look at the schema. So see here, sales fact table is a fact table, and you have a dimension tables called as a time, item, location, and the branch. Time, location, item, and the branch. So you have time, branch, sales fact table, item, and then the location. So all these attributes you see here, item key, item name, brand type, and the supplier type, you have all the different attributes for the location. And whereas a time key is a foreign key from the time dimension, item key is a foreign key from item dimension, branch key is a foreign key from branch dimension, and the location key is also a foreign key from the location dimension. If you see what are all these units sold, dollars sold, average sales, these are all the things which are the measures. So always there will be a one-to-many relationship between the fact and dimension and the fact table. So here the item table and the location table, see, look at it. If you try and represent the data, for item dimension, so what happens? Let's say I'm representing the data for item dimension in the denormalized format. You have so many attributes. I'm not representing all of them. Item name, let's say brand, and you have the type as well. So item name, type, brand type, and the supplier type. Supplier. Okay, let's take out the type. Brand type. Okay, let's take out the brand at least. Okay, let's try and represent the data. So let's say you have an iPhone 4. iPhone 4 is an item name, and the type which comes, this is a mobile category. Under the mobiles, who is supplied? Apple is the supplier who supplies it. So if you try and represent iPhone 4S again, iPhone 4S. So this is also again a mobile. So this is a supplier is a Apple. So what's happening? And you will have different supplier attributes. Let's say you have a supplier name and supplier full name or supplier state, from where it is applying, and the different attributes, like all the different attributes about the supplier. So if you try and represent the data, see here, entire supplier information will get repeated. Let's say you want to even represent something like this. Let's say you want to represent Galaxy tab, and this comes in the mobile category, and the supplier is a Samsung. So if you see, entire supplier information is getting repeated. So let's say you want to represent LCD TV, 32 inches. And the item name will be different, some other name, and this is comes in the TV category, and you have a lot of suppliers who supplies that. So if you see the supplier information, whatever you are getting representing is getting repeated. Only the item name and the type is changing, but the same supplier information is getting repeated. That means you have a lot of duplicates in the supplier. You have a lot of duplicate data, redundant data in the supplier. So the normalization is nothing but keeping the supplier information in the another entity, and then create a relationship between the supplier and the item. That is called as a normalization. Now, if you see here, same star schema is converted as a snowflake schema. If you see, item is being divided as two entities. One is the item, another is a supplier. So wherever you have a redundant data, and you can normalize it to save the memory. So here the item and the supplier is divided to, and the location and the city are also divided into two entities. That means item, previously it was a denormalized entity, and you made it as a normalized entity, and the location was a denormalized entity, and then you have made it as a normalized entity. So in the snowflake schema, few of the dimensions are denormalized, normalized, and whereas the star schema, all the dimensions are denormalized. So when you more normalize, the number of tables in the schema will get increased. So star schema is always advantageous because you'll have a less number of tables. Advantages of the star schema is it will provide highly optimized performance for a typical star queries. typical star queries. Which means in the star schema you have a less number of tables. Let's say I have a total 5 tables. I hardly require 4 joins to retrieve the data from all these tables. But if you go to the Snowflake schema, so the number of tables are more, so the number of joins are also more. So it makes your query little complex. It makes your query little complex. So that is the star schema will give you an advantage in terms of a performance, and the Snowflake schema is a kind of a, Snowflake schema is performance-wise, it doesn't give you the best performance as compared to this because the number of tables in the Snowflake schema is more. So the disadvantages with this is increases the number of tables and makes the queries much more difficult in the Snowflake schema. Then you might ask the question, why to design the Snowflake schema? Why can't we go every time the star schema can be designed? So most of the time in the real time, so you'll have a star schema which will be designed but in few cases where your item table will be growing. I mean, if your dimension table is growing with a more number of rows, just like your fact tables, we just can't handle the dimension if it is growing very fast. In the sense like, let's say you are think about the Walmart retailer. Probably they might be selling close to 1 lakh items, and think about how many suppliers are sorry, I mean when I say 100k records, 100k items, and when you talk about the suppliers who are actually supplying them, and if the historical data is being tracked for every change, then a single dimension itself will have close to 2 million records with this. So whenever your dimension table is growing very fast, in that case, instead of storing the data in the denormalized format, we normalize the entities because growing dimension also causes the problems because it occupies the more memory and it gives you all the redundant data. Wherever you have a fast growing dimension, not about the slowly changing dimension, wherever we have a dimensions where it is very fastly growing, in the sense today we'll be selling one item, tomorrow we'll discontinue that. Today we'll be selling an item with one price today, tomorrow we'll sell it with a different price. So every time there is a change in the attribute, you have to make an entry. So that is how, so since these kind of dimensions, we can't store the historical data, and then we can't keep these kind of dimensions growing, then that's the reason we normalize this kind of dimension. Suppose let's say item is which is very fastly growing, then we'll normalize these kind of dimensions and then keep a Snowflake schema. So wherever you have such kind of dimensions which is very growing, so in those cases you can normalize the entities and then keep it. So the Snowflake schema is performance wise a disadvantage, but you have to take the burden of performance when you're actually normalizing the entities. That is where, because it's fastly growing, and in those cases there is no option of other than going for a Snowflake scheme. So the star schema or the Snowflake schema, whenever you design, it's nothing but you're going to design the dimension tables and the fact tables and the relationship between the dimension tables and the fact tables. So the Ralph Kimball has actually given a few steps whenever you're designing a star schema or a Snowflake schema. So you can think about all these steps. I mean, you can follow these steps whenever you're designing it. First, identify the fact table name according to the subject area. So let's say you're designing the fact table for a subject area sales, we name it as a fact underscore sales. If you are designing it for a marketing, we name it as fact underscore marketing and all those things. And identify the grain of the fact table, which is very important, like at what level you're storing, whether you're storing at the month level, year level and all those things. Next thing is the identify the dimensions which are being used, item dimension, time dimension, model dimension. So all those dimensions you have to identify and select the facts. Facts are nothing but your measures. You have to determine the measures and the dimensional attributes. Dimensional attributes also should be decided before starting with it. So that is how you are going to design the star schema. This is the steps which are given by the Rolf Kimber. And we have two types of dimensions. One is called as a conform dimension. Conform dimension. Let's say the conform dimension is something that which is very simple one. So let's try and understand what is a conform dimension. So we know that always there will be a relationship between the dimension table and the fact table. Dimension table and the fact table. So you have two fact tables. Let's say you have two fact tables called as F1 and F2. F1 and F2. And I have a dimension table called as a time dimension. I have a time dimension. So assume that you have a fact table called as a fact underscore sales, and you have a dimension called as a fact underscore marketing, So I have a dimension which is shared by the multiple facts. I have a time dimension which is in relation with fact underscore sales, and I have a time dimension which is in relation with fact underscore marketing. What is this dimension name? We have this dimension name is a dim time. This dimension name is a dim time. So the time dimension is something that which is shared by the two facts. A dimension which is shared by the multiple fact tables is called as a conformed dimension. A dimension which is shared by multiple facts is called as a conformed dimension. So that is called as a conformed dimension. When you talk about it, so a cube which contains a dimension F1, D1 and D2, D3. Another cube contains F1, D1, D2 and D4. So if you see the D1, D2 are the conformed dimensions. D1, D2 are the conformed dimensions. And the other dimension is called as a degenerated dimension. So the degenerated dimension is something that physically it will not exist in your schema. Or physically it will not just exist in your warehouse. Rather, it exists as part of the fact table as an attribute. Let's say you have an attribute called as an invoice number. Invoice number, which you are just storing it in the fact table. For just a reference, you are storing the invoice number and the order number and all these things. That attribute is actually descriptive in nature. So that kind of an attribute together, I mean, it's called as an invoice number or order number, which is called as a degenerated dimension. So the degenerated dimension is something that which physically will not be existing. We'll just keep that attribute as part of the fact table. So that attribute itself is called as a degenerated dimension. So this degenerated dimension is often designed to provide the direct reference back to your OLTP systems without maintaining the separate dimension table. Without maintaining the separate dimension table, we'll just store that attribute in the fact. So that is how you design the star schema and the snowflake schema and the different types of measures and different types of. So whenever you are designing the dimensional modeling process, you have to determine what kind of dimensions you have to create and what are the attributes of the dimensions, what is the fact table and what kind of dimensions you want to include in the fact table and what kind of measures, and anyway the relationship between this and this is it. So where you have to go for a snowflake, where you can go for a star. So that is how the star schema and the snowflake schema will be designed in the real time. So whenever you want to design the data model, so you're going to design either star or the snowflake, depending upon your business requirements, right? So that completes your dimension modeling process. And in the next class, we will talk about Informatica and Informatica architecture and with different hands-on labs. So any questions so far?